Hi folks, hello everyone, and welcome to Iron Beetle. As usual, this is a weekly show at 5 p.m. UTC, live on Twitch, and then what's with my hair? Well, it's okay. And one recorded on YouTube, where we look inside Beetle database. And when I say look inside, I don't mean that we kind of just go through some of key points and keep it very high level. No. We go right in the deep end. We try to understand every single line of code. And well, occasionally I don't understand line of code. I have to fumble live and figure out what's going on. Occasionally we found a bug or stuff like that. So yeah, that's the usual thing. And today, we continue doing our looking inside table thing. And we finally complete our slightly interrupted arc about the request protocol. So as a reminder, in the architecture, Beetle doesn't talk directly with mobile phones or website. Beetle talks with API gateways. So the API gateway exposes some kind of HTTP API, websites, mobile applications, whatnot, connects to that HTTP API and submits individual financial transfers. The gateway then aggregates individual financial transfers into large batches of 8,000, 5,000 transfers, and then sends those batches as a single request over trusted connection to Beetle cluster. Because in Beetle we are not allocating memory dynamically, and we have a known upper limit for everything in the database, we have to design back pressure in. It cannot be an afterthought because, well, there's no infinite memory. And the way we do it is that we say that every client, so every API gateway which talks with Beetle, can have only a single request in flight. And I think we already looked at how we maintain the state of which clients are connected to the cluster, which clients are not connected in the so-called client sessions. And I think we've also looked at how replies are actually stored on disk. Actually, okay, I'm actually not sure whether we looked at that last thing. So let's quickly refresh. So we have client's replies, and we have reads, writes, and we periodically and we can ask to read a particular reply. Yeah, I think yeah, we definitely covered it. We definitely covered like this split into read reply sync and read reply. Okay, so the only thing we haven't covered fully is how client handles retries, or rather, we looked at this last time and we actually found a bug in the implementation. So let's see. In the client, there is on request timeout, and the job of the on request timeout is to retry request against the cluster. Because again, this is a distributed system, so whenever we are sending a message to a cluster, we have no way of knowing whether a message was received or not. So if we haven't received the reply, then we have to retry. And here we've noticed this, like, rather logic, as logic tends to be, where we round robin through members of the cluster. So normally we send our request to the primary, and the primary is a view number modulus the replica count. So very simple. But if we are retrying, then, well, we try to go to the next replica in this ring of replicas. Super simple, super reasonable. The problem is that on the replica side, we have this ignore request message function, which says where we should be ignoring reply. And there is actually this okay, where, yeah. No, it's not this. Okay, so it is not duplicate. If it is not duplicate, okay, it was definitely much easier to find this bug yesterday. So we were comparing view numbers there, and there was a case for view different or view, okay, maybe it is not ignore request message duplicate, then, well, it cannot be upgrade. Well, maybe it is preparing. Well, okay, it cannot be preparing. Okay. Huh. Okay. Okay. So let's just then read this from the start. So remember, like, the strategy that our client uses is that it round robins across members of a cluster. And my claim is that there is a bug where, if a replica receives a request and the replica is not a primary, it will just drop the request on the floor. So the effect of our round robin is that we uselessly submit our request against members of the cluster until we round rob through the entire cluster to the primary, which feels completely useless. And okay, yeah, because it is ignore request message backup. Okay, now I will find it. So yeah, we have this. So if we are a backup and we receive a request, if the view is the same, then we simply drop a message on the floor. And this is obvious bug. And again, this is one problem with naive deterministic simulation testing is that It can tell you when your code is incorrect. It can answer binary properties like, hey, is this theoretically available? But out of the box, it doesn't actually tell you performance of the code. So obviously this is a bug. We just dropped the message on the floor and we require the client to send a useless round of messages. The client it would be strictly better if the client simply waited longer and then retried against the primary. But you cannot actually immediately see that bug in the VOPR because formally we are still available. Eventually the client will retry against the primary and will get its request through. Okay, so we still can. Okay, let me maybe make this font slightly bigger. Okay, yeah, this is better. So I'm right now I'm going to show a feature of VOPR I've been working on for the past few weeks, which is VOPR performance mode. So now we run VOPR with seed92 and we pass -- performance flag. And once it finishes, now you see actual message statistic for this VOPR run, and also notice that in this VOPR run, actually all the fault probabilities are at zeros. So performance mode is two things. First, we disable almost all the faults, and second, we actually count logical performance. How many ticks did it take for us to finish this scenario, and how many request messages have required? So you see, we needed 276 prepares, 276 requests. We need more prepares because prepares are replicated across the ring, so it should be roughly 6 times more. And indeed, if I multiply that by 6, I get 1 3 something. Okay, that makes sense. But notice that this is with packet loss probability equal to 0. So what I'm going to do now is I'm going to find my editor. Okay, I found my editor successfully. Actually, isn't? Okay, yeah, I feel this is also on the small side. Okay, that should be better. So let's say that let's also reduce client's count to 0. So to 4, well, to keep it really simple, let's reduce client count to 1. Okay, so 1 client, no errors. We take some time to compile stuff and then run. And yeah, okay, so we see 6K ticks for 1 client. Now, we are going to introduce some packet loss. Let's say that we are losing 10% of our packets. Okay, so now we should see significantly more ticks and significantly more requests. And yeah, you see even in the wall clock time, in the wall clock terms, it takes significantly more requests for us. So you see, although we lose only 10% of messages, we actually needed more than twice as many requests, simply because whenever we lose a single message, it also so happens that we will need more than 1 retry to round robin the thing. Okay, so how do we fix it? Well, now I will show you a magic trick how you could fix complicated bugs. So you see, we need to code a new algorithm. So I'm going to say get --pop, and that's it. because actually the code I'm going to show today is already in main, but I want to kind of like discuss the diff, like how do we fix this problem? Okay, so I guess we should start with this on request timeout. So how? Okay. So you see this is mangled highlighting here. And here, by the way, so ZLS still has state problems. It still can when you switch branches, when you pop things off a stash, it still can get confused as to what is the actual state. So that's not good. That needs to be fixed. But okay, we can live with it. We can just reload the window. But like, yeah, this is why you need this is, folks, why you need strict serializability to not have like this kind of anomalies. Okay, yeah. So basically, let's see what we do here. Okay, so this is the thinking. One thing so one way you could imagine solving the problem of this like useless round robin is that, okay, let's say that client round robins and sends a message to a backup, and that backup is not a primary, so it cannot convert request into prepare, yada 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 yada. But what it could do is that it can actually forward the request message at a primary. And like you see that it sounds kind of like neat. Like, you know, the clients don't have to know who the primary is. They can talk to like whatever node in the cluster, and then that node in the cluster will just forward messages. But that violates one of the false prey to one of the fallacies of distributed computing. And that fallacy is that, like, you know, bandwidth is limited. And that is not true. Like, actually, like, network is a resource, and you should use as little network as possible. So if you just, like, you know, do work for the client and forward their messages, what you did is that you increased 2 times the amount of bandwidth you need to process this message, because, like, you know, instead of client directly sending its stuff to the primary, now the client sends its stuff to the backup, and the backup replaces the primary. So we kind of like do twice as much work. And second, we also increased the latency, because now there is like extra round trip in there. So that's not good. The invariant we want to maintain is that the client always talks to the primary. And this is like the first change here, that whenever we are resending our request message, we are going to resend it against the primary. That creates a different problem. What if the primary died? So, okay, let's say we were in view number, I don't know, 7. So replica number 1 was a primary, and we were sending happily requests to replica number 1. And suddenly, for our, I don't know, 30th request, we didn't get a response within a reasonable time. So what do? Okay, so our first assumption is that primary is down. So we try to just resend the request. Okay, we send the request. Okay, maybe we get a response, and that means that, okay, we just lost a single message. So that's good. But let's say we actually haven't got a response to our second retry. So we do a third retry. And like eventually we kind of like begin to suspect that what happened is that the primary we used to talk to actually died, and the cluster did a view change. So now there is a new machine who is a primary, and we should be talking to that. But we don't actually know the view. Like we kind of like need to learn the view number from the cluster. And, you know, it would be reasonable to say that you could learn the view number from the X primary from this replica 1. But, well, if it is that, then it cannot inform us about our view. So This is the second idea. And the second idea is that if you are retrying, so you are resending your large request message, which is like 1 megabyte, to the primary, but at the same time, you also make a tiny ping message and you throw that ping at like random or round robin replicate in the cluster. So basically, like there's like two reasons for why you didn't get a message. Either the message itself got annihilated, and that means that this retry will save you, or there was a view change. And then this ping will respond with a pawn, which lets you update the view. So by the next retry, you actually will be retrying against the true primary of the cluster. Okay, and that in turn allows us to massively simplify code in the replica. So basically, we delete this whole ignore request message backup stuff and just say, okay, if we have backup, we just always ignore and never try to like forward it or inform the client or whatever. Okay, so that is the idea. The question is, does it work? Okay, so let's try to rerun this same performance test with this same seed. And well, let me double check that we are, okay, we still have a packet loss ratio of 10% here, and we still have one client here. Okay, so let's see whether this is better or not. Well, I mean, the code is merged, so I really hope that it is better, because if it is not better, then it means that I have messed up. Okay, so first of all, we are definitely better in terms of ticks. So instead of like 35K, we need only 10K. And let's also see at the number of requests. Okay, so here we have 560 requests, and here we have 348, which I think is still larger than 10% of this. But remember that either a request or a reply can get lost. So, okay, like, I guess on average, you would see 50 like requests without replies. So that should be 300. I think we're doing slightly, okay, we are doing 350. Okay, honestly, I don't fully understand like why we get, well, okay, we lose 500 and then we lose 50 for retries, and then I was thinking that maybe the rest is like, double retry. So like we retry and lose message twice. But okay, if we lose 50 due to retries, then like retry would be 10% of that, and that would be 5. Yeah. So okay. Okay. I guess this is lost prepares. I guess it could also be the case that some prepare in the replication ring gets lost, and then okay, now it is actually okay. It makes sense for me. So actually, there is like 4 messages which are critical. So one is request, like obviously if you lose a request, then cluster doesn't know that there was a request. Then of course there is a reply. If you lose a reply, then the client doesn't know that the request committed. And then while request is converted to the prepare is replicated along the ring. So if we lose prepare on the first leg on the ring or on the second leg of the ring, then we will have to wait until prepare timeout fires and we do a retry. If like the third ring of the prepare replication breaks then it is not a problem because we have prepared our case from the primary and from 2 of the replicas. And similar, if any of the prepare OK messages get lost, it is also not a problem because if the prepare itself gets replicated across a cluster, well, we'll just get prepare OK from other replicas. And this is actually another bug. Like, it is problematic that a loss of a single prepare forces us to do a retry, and maybe we will look at this today or maybe later. Anyway, but okay, so this is hypothesis that there are 4 messages for each request which are critical to process requests without timeout. So we have something like 250,000 requests. And 10% of the messages are lost. So I mean, I'm of course like not doing like, you know, proper like multiplication of independent variables or whatever, but if I just like eyeball it, then okay, we have 250,000 requests and we have like 4 messages per request, which are critical. So we have 1,000 of critical messages, and 10% of those critical messages are lost. So 100 messages, 100 critical messages are lost. Of course, like, you know, some of the critical messages are for the same request, so it's not a problem, but okay. Let's assume that they are like different, and that means that we expect to see about 100 retries, and this is exactly, this is in fact exactly what we are seeing. So we had 260, and we got 338. And this is, by the way, this is like what we've did right now is like critical whenever you are looking at the benchmarks, because you see, like, the purpose of the benchmark isn't to tell you the number. Like, this is never why you are benchmarking. You are never benchmarking to get the number, to, like, you know, do A/B testing, like which is better, which approach makes the number go up. No. Like, the way you figure out which code is more efficient is that you understand precisely what goes into performance. And like the way you like write fast code is that you build a complete theory of the runtime behavior of the code in your head. And the role of the benchmark here is to validate or disconfirm your mental model. So again, the goal of benchmark isn't the raw number. The goal of the benchmark is to tell you, the human, why the number should be the way it is. And this is like, you know, we kind of like, we could say that, hey, kind of like, there's like 560 here and like 340 here, so this is better. But this would be like poor engineering. Like, the good engineering is to like look at this like 340 and think, okay, is this a reasonable number or not? And then you look at the baseline and see, okay, the baseline is like 250, and we are losing 10% of the messages. So we expect to see 270 there, not 350. So okay, something is wrong. And then you realize that your mental model is actually incorrect, because there is like request and reply. So okay, you should lose not 25. You should need 50 rather than 25 retries. And then realize, okay, kind of like 50 is still too little, because we need like 100. Where is another 50? And then you realize that wait a second, there's actually 4 critical messages that you need to get the request out of it. And then the numbers align and you realize, yes, now you understand the issue. And while doing it, you understand that, hey, actually, isn't it a problem that to get a single reply without any kind of a timeout, you need 4 critical messages to not get dropped? Like, you know, that's like greatly multiplies the amount of load you say. So again, let's compute it. So we have only 10% loss, but our requests went from 350 to from 250 to 350. So this is like, we lose only 10% of the messages, but we multiply our like load by 1.5. So this is definitely not good, and that's why we actually need to change our application protocol to make sure that a loss of any particular single message doesn't cause these kind of issues, so that we can tolerate more faulty networks. Okay. And this actually, I think, completes. Do we have to do? Okay, where is to do? Okay, let me quickly find it. Okay, this is my terminal. This is not what I want. Just a second. I'm going to find. Or maybe I'm not. Okay, something. Okay, found it. Found it. Okay, so here it is. Yep. This is how to do stuff. So okay, I think we've covered client sessions. We definitely covered grids block missing. Okay, so what are we going to do next? We can go. Okay, actually, any suggestions in the chat for what we should cover next? Because I mean, I want to finish the request protocol. We've just finished it. We still have half an hour. I can pick myself, like, the topic, but like if there is some suggestion in the chat, we could go for it. Okay, so one option is that we could dive deeper into that better retry protocol, which should fix like the 10% loss equals 1.5 network amplification, but I'm not super keen on that. Upgrades are super cool, but okay, that's completely different. Okay, maybe okay, this is interesting. Should we finally look at the VOPR? Because today, last time we were fixing a bug in our simulator live, and today we actually looked at the performance VOPR. So maybe it's high time to start explaining the VOPR. Okay, yeah. No suggestion in the chat. So I assume you are all happy with doing the VOPR thing. Okay, then let's get the fresh code and see. Okay, suggestion from the chat. Can you show how to run the VOPR? I mean, I've already shown you. Like, this is how you run. So like a Zig build VOPR, but probably I can share a couple of tips here. Okay, and let me actually get into my like serious type and serious coding sit-in pose. Okay, yeah. Let's start with the interface. The basic way to run VOPR is you say Zig build VOPR, and you pass there's the release line, because usually you won't compile VOPR with optimizations so that it can like run faster, because usually, especially if you have non-zero amount of faults, so not in performance mode, it actually takes a lot of CPU time to churn through a particular seed run. So you might want to run it with release and okay, LLVM bean, LLVM, okay, yes, you see that, okay. This one was pretty fast. This one also was pretty fast. And okay, one more thing is that notice that every time I run it, you get, oh yeah, this one is slow. Every time I run it, I get a different result. Because when I run VOPR without arguments, it tries a random seed. So the way I usually run VOPR is like this. I have, okay, not too fast. I have this end utility because, I mean, I don't know how to write shell scripts. I don't know neither bash, no fish, no new shell, no nothing. Like only Zik, only Rust, a bit of like Kotlin, Python, maybe TypeScript here and there, but definitely no shell. So I don't know how to write a for loop in shell. But I mean, I know how to write Rust, so I wrote my for loop for shell in Rust. So N is my short utility. Actually, we can probably just show it. Let me go in config and tools. Okay, this is okay. This is really a small tool which just okay, and also I haven't set up Talon shortcuts yet. Okay, so this little tool is just like, you know, takes a number and then it runs the program n times while the program returns 0. As long as program fails, these tools will stop and say, hey, like you got a failure. And this is perfect for running VOPR because I just say, hey, I want 1,000 runs, or I want 65,536 runs, or whatever. Okay, so that is the main thing. And like eventually, eventually VOPR will find some problem. I don't know. Let's introduce some bug. Let's say that inside replica, jump view, let's assert that header view is not equal to 9. I don't know. Should fail. Yeah, let's see how long will it take to fail. Maybe one run, maybe more runs. But you'll have to wait a little bit. And a little bit more. Really, like someone got the right fast backend for native code. Like really, like this is not good. This is like this destroys productivity. Okay, yeah. Okay, yeah. You see, this is how it works. So also, someone should teach me how to scroll with the keyboard in my terminal. Yeah, you see, we crashed on the third run, and but you know, at the start of the run, VOPR prints the seed. So if you want to recreate the result, you just pass this seed as an argument after double dash. And yeah, we are failing. And because we are compiling with release, you don't get like super useful error message here. But that's the thing. When we do have a seed and we know that seed fails, we don't care about VOPR performance as much. So we could run it in debug, and that should be faster to compile, and it should also provide us with a better error message. But yeah, obviously it takes slightly longer to run. Okay, and here we see, yes, we fail at the assert we've just introduced. It would be really fun if we actually found some related bug, but no, that's rather unlikely. Okay, so that is the basic thing about the VOPR. And then there is like one more thing. Okay, let's say that the bug is like not that easy, let's say that we want to get more logs out of it. Then we pass -d release, because emitting logs is actually very slow, and for logs you do want a release mode. And you pass -d VOPR log equal full, and you want to redirect the logs to some file. So we redirect this stuff to log.vopr, and well, while this is running, we can see that. Oh, okay. It is not yet running, because I think it is still compiling the stuff, because we compile with release, and we cannot reuse our previously compiled release build, because the log level is set at compile time, which, now that I think about it, is kind of like maybe not right, because we already have runtime login for. Okay, yeah. So you see, it was quite a bit of logs. So this was a relatively short run, but we got like 150 megs of well, MIB bytes. Let me not be ashamed of saying MIB bytes. MIB bytes, 145 MIB bytes of login, which is like a lot. But well, if you have a fader, that's a lot to work with. Okay, so I think that is all there is to VOPR interface. Well, and then there is like this dash for performance mode, which we looked at today, which disables most of the faults and prints memory statistics. Oh, actually, okay, actually, there is also this light thing, which runs the smallest cluster, and it doesn't look for liveness. So basically, kind of like light is like poor man's minimization. Is that, like, you know, if you break VOPR in the light mode, like you broke it like really badly. But like a failure would be easy. And like the full mode tests larger set of faults. Okay, so let's then dive into the implementation of VOPR. Like how is it possible? And this is actually, I mean, VOPR. Okay, so let's remove this. VOPR is a lot of code, and it can be pretty intimidating, but it is relatively simple. So let's look at the main loop. This is sort of like the main loop. Like in a while, we just do our tick thing, and that's it. And in the simulated tick, the main thing we do is that we tick cluster. So what is a cluster? Cluster is a struct which contains like 6 copies of a replica. And oh dear. Okay, so this used to be simpler. Okay, so kind of like what this tick morally does is that it says for cluster replicas replica.tick, but it is actually slightly more involved than that. Okay, so let me pause for 5 seconds here to grab a cup of tea and to think about like how we are going to cover it exactly. Okay, I'm back. And I think that I actually don't want to start diving too deep into the code of VOPR right now, because there's a lot of code and it will take me a lot of time to explain it, and it deserves a whole new episode. And because I did a 3-hour stream yesterday and then had a very poor sleep, I actually don't want to carry on much longer than our usual episode length today. So let's say that next time we'll be diving into the guts of VOPR. So let me just explain on the high level how this works. And the main thing here is that we don't do any threads. We don't do any processes. We don't do any distributed, like really distributed kind of things. We mock literally everything. So in production, Tigerbeetle runs a single thread. In the VOPR, we run 6 replicas. But we don't run each replica in a separate thread. We use one thread to run every single replica. And that is really kind of like the key to understanding this architecture. So you need to be very precise about your input-output, such that you don't even have to spawn threads. You can do this whole thing right in the same event loop. And the way this works is that, like at a super high level, is that our replica, where is our replica type? Yeah, our replica is actually generic. Our replica is generic over state machine. The main thing for VOPR is that our replica is generic around like message bus, storage, and time. So a message bus is network, storage is disk, and time is like time low. So these are the 3 sources of input-output. In our VOPR, we will replace them with test implementation. So you see, for example, for storage, we have SRC storage, which is like our production implementation of storage, which uses IO uring to actually read from disk. But then there is also test and storage, which is in-memory storage with simulated faults and latency. Quick tip. When you write documentation commands, do start every large documentation command with one line summary, because, well, then someone folds the thing in the editor, they still have like summary as a proper sentence. Okay, so storage. Okay, it's even a struct. It's not even generic in itself. Okay, and that's kind of like a gist of it. We abstract all IO, and this allows us to run everything in a single thread, and then we just go and run everything in a single thread. There are a lot of details to that, and I would guess that we'll need more than one episode to cover VOPR, maybe even 3, maybe even more. But let's say that this is for Matclad from the next week to explain, because really I should take some sleep probably at this point. Okay, so thanks for watching. Sorry that this stream was slightly shorter than usual, but on the other hand, actually you got twice as much information, because you've learned both. Well, actually, I mean, you've got like 3 times the usual amount of stuff, because you've learned the old broken request retry algorithm, you learned the new improved request retry algorithm, and you learned quite a bit about how to run VOPR and its overall structure. And for like the deep details, please join me at the same time, the same place next week. Thanks for watching, and goodbye.